All right, we're going to take another example of finding the area bounded by a polar graph. This time we're going to look at 4 minus 4 cosine of theta. So this one is not going to be a rose petal, so actual graphing of it is going to be nicer. Even nicer, the theta is by itself, so we can just straight up use the 0, the pi over 2, the pi, 3 pi over 2, and 2 pi for graphing our cosine graph here. So we'll first graph it like we would have in pre-cal or trig. So we'll use those values, and when we plug them in, it's going to give us 0, 4, 8, 4, and 0. And we'll go ahead and plot that and then graph our cosine graph. So one way you can think of this is it's the regular cosine graph. The amplitude is 4, so it's going to be stretched. The negative 4 is going to cause a reflection over the x-axis, and then the 4 on the outside, that 4 there, it's going to cause a vertical shift up 4 units. So we're going to go ahead and graph that, and we'll take a look at what that looks like, and that's actually going to help us when we graph this. Now, it's going to be the artist's fault that this doesn't quite look symmetric, but you can use your imagination and pretend like, yeah, both sides are symmetric. So if we can just graph half of this in the polar coordinate system, then the other half will be exactly the same. Follows what our graph's doing here. So we'll install our polar coordinate system, and we got to go all the way out to 8. So we'll have each ring represent 2. We start out at the pole 0, 0. At pi over 2, we're going to be up at 4. At pi, we're going to be out at 8. And notice that we do have like a horizontal tangent here, so that's, I'm trying to illustrate that flatness here. And so we're going to start at the pole, and we kind of have the rest of the horizontal tangent here if we continue our cosine graph. So it's going to be a little flat around the pole, and then it'll kind of curve out. If we want it more accurate, then we plot more points, but we don't want a super I mean, I guess you want, if you want, but we kind of just want a rough sketch. So it'll kind of be curve out, and it'll look something like that. Okay, and because it's symmetric, the other side is going to look the same. And what we're going to do is we're just going to find the area of the top half, and that should be enough. And so how this curve is sketched, is we start at 0, and we'll go to pi, and if we wanted to keep going, it takes a full 2 pi to go all the way around. So we're going to go 0 to pi for our limits of integration. And the integration isn't real difficult. We're going to use the power reducing formula once again to find the area. So we'll do that on the next slide here. So your limits of integration are 0 to pi, so that's going to give us that upper half of this figure. So there's two halves, so that's why there's 2, and then 1/2 part of that formula. 0 to pi, and then 4 minus 4 cosine of theta quantity squared. Okay. What I'm going to do is I'm going to mention that this can be written as 4 times 1 minus cosine theta squared, and so 4 squared is 16. So 16 is going to pop out at the integral, and then we're going to expand 1 minus cosine squared. Okay, so it's going to be 16 integral from 0 to pi 1 minus 2 cosine theta plus cosine squared theta d theta. Now the cosine squared theta, that's going to give us a 1 plus cosine of 2 theta over 2. So what we're going to do is we're going to grab the 1/2, that's going to join the 1 and make it 3 over 2, and then we'll still have a cosine of 2 theta over 2 left over. So we're going to have a 3/2 minus 2 cosine theta plus cosine 2 theta over 2. So that is the work that we'll do in our head here. So you have 16, 0 to pi, 3 halves minus 2 cosine of theta plus cosine of 2 theta over 2 using your power reducing formula. We'll go ahead and integrate. So you got 16 out front, 3 halves theta minus 2 sine theta plus not cosine, sine 2 theta all over 4, and then we're going to evaluate that from 0 to pi. Now when we stick 0 in and pi in, we're going to have the sine of 0 and the sine of 2 pi, both of which are 0. Or if we plug in 0 and pi in here, we're going to have 0 and pi. The sine of both of those is 0, so the sines aren't going to contribute anything. Essentially all that's going to matter is we're going to install the pi. The 0 won't do anything either. So it's going to be 16 and then 3 halves times pi. And that's going to give us 24 pi as the complete area in this figure here. Okay, this was a little bit easier because the sketching was easier. We'd have to go through sketching all the pedals and finding the tangent lines, and the limits of integration were a little easier to find in this example here. If I have time, I'll do another example or two where we're looking at two different polar graphs and maybe find the area bounded between two polar graphs.